I'm really pleased to be here. This is a great venue and a great topic. Unless you've been hiding under a rock, you've realized that AI, and in particular deep learning, is changing almost every aspect of human life. You know, in the internet, every time you upload a photo to Facebook, they run it through a half a dozen deep networks looking for inappropriate content, copyrighted content, tagging faces, et cetera. When you talk to Google, you're talking to a neural network, and that's why the speech recognition is so much better. When you travel, you can translate language by just pointing your phone at the text, and it comes out in whatever language you're most comfortable with. It's making doctors more effective. The goal here is not to replace doctors with neural networks, but to empower them so that a clinician with a neural network can interpret medical images better, whether it's for skin cancer, whether it's for breast cancer, whether it's looking at retinas for various forms of eye disease. And also they're mining data of various symptoms and signs, patient histories, and helping doctors make better diagnoses. Media and entertainment, it's completely changing how people produce content. Security and defense, it's easy to train a network for what's normal. Anything abnormal is an anomaly, gets flagged. And one thing we're very excited about at Nvidia is the prospect of saving some of the 1.3 million lives lost on highways worldwide each year by applying neural networks to autonomous vehicles. Now, as a computer architect and a hardware designer, what's particularly exciting to me is that this revolution was enabled by hardware. Most of the algorithms we use, deep neural networks, convolutional neural networks, training them with backpropagation and stochastic gradient descent, were all around in the 1980s. I actually took a course when I was a PhD student at Caltech from John Hopfield, who was visiting Caltech at that time on neural networks, and built a lot of these networks, and concluded that we didn't have enough computing power to make them useful, which was correct in the 1980s. The other ingredient you need to make these things work is lots of data. We had that around the early 2000s, and the ImageNet competition was running for a long time before deep learning took off with million image labeled sets. But the missing ingredient, and the spark that really ignited the fire that is the current revolution in deep learning, was having enough compute horsepower to train these models on these data sets in a reasonable amount of time, where people defined reasonable as 2 weeks. And once that happened, it took off. Now, since it's taken off, we have this issue, and two of the previous speakers have had this little cycle of better models, more data, better results, that deep learning is now gated by hardware. We need to continue to produce faster solutions for both training and inference to enable people to run bigger models on more data. This shows sort of the increased compute complexity for images going from 2012 to 2016. So a 4-year period, you need 350 times as much performance. For speech, over a shorter period, it's 30x. For machine translation, 10x. And so we have to continue to deliver better hardware solutions. But Dave Patterson actually showed you this exact slide this morning. Despite the fact that a particular company is in denial about this fact, Moore's law is dead. If 2 Turing Award winners sort of call it, I think it's a done deal. You can put the defibrillators away. Now, to give you an idea of a little bit of what's going on, and Clement talked about a bunch of this in his talk, let me just show you one brief example of how we use machine learning and what the compute complexity is. So we use a network called DriveNet, which is very similar to ResNet for our deep learning perception. We have 12 cameras on the car. For each camera, we do many things. We do detection. We detect free space. We have 2 independent calls of where it's safe to go, one by detecting what's safe and another one detecting what's not. We find lanes and predict a path that goes into our path planner as a suggested route. And we do this in all directions from 12 cameras. This is putting all 3 of those together. And we do it in all kinds of weather. So we do it at night, during the day, in the rain, in the snow, and have tested it on lots of real and synthetic scenarios that happen all the time. Now, if you look at the computational complexity of doing this, let's start with ResNet 50, because I don't want to release the details of DriveNet. ResNet 50 is very comparable. To run an ImageNet-sized image, that's roughly 8 billion operations to feed one image into an inference coming out. So if you're to do that at 30 frames per second, it's 1/4 of a teraop to run one camera through one network But our cameras aren't ImageNet cameras. In fact, I don't think anybody has ImageNet-sized cameras that are 225 by 225. Our cameras are HD cameras, and in the very near future, they're going to be moving up to 4K. But at HD, it's about 10 teraops per camera per network. We have 12 cameras, 4 networks. Actually, we have more than 4 networks, depending on how you look at it. But the 12 times 4 is a good number. So the computational complexity here is really enormous. How do we solve that? Well, today we do it with GPUs. And I'll talk a little bit about the evolution of GPUs for deep learning. It's actually an interesting kind of co-evolution that's going on. And the current GPUs are very much designed to be deep learning accelerators. If you're training, the absolute best machine on the planet for training, and I'll get to the MLPerf results shortly, but as certified by MLPerf, is a Tesla V100 Volta Tensor Core GPU. And what makes it really good for training are 2 numbers on this. I'm not going to go through all the specs. One is that it has 125 teraflops of Tensor Core performance. That's FP16 performance. And we provide a software package called AMP, Automatic Multi-Precision, that does scaling. So it will take almost any, in fact, we have not yet found one that it doesn't do reasonably well on, almost any model and automatically scale things so you can run the training in FP16. The other number here that's really important, actually 2 of them that are important, is the nearly a terabyte per second of HBM bandwidth. Because a lot of these models, especially as your batch sizes get up there, the activations don't fit on chip, and you're actually running the activations through that memory interface, and a conventional memory interface can't keep up. And then for scalability, we have 300 gigabytes per second of NVLink bandwidth, so we can connect these together into a training supercomputer. And I'll show the MLPerf scalability results shortly, where we won every category we submitted to. Now, the reason this is so good at training is it's very much a special purpose device for training. But unlike a TPU, where Google basically built a big 256 by 256 matrix multiply unit, what we decided to do was to take a very flexible, programmable engine, which had a very capable memory system, which is half the battle, and add an instruction to it. And the instruction we added was HMMA, half precision matrix multiply accumulate. And it does what's shown here, in that it takes 2 FP16 matrices, multiplies them together, and adds them to an FP32 matrix. And because it does 128 floating point operations, almost all of the energy goes to doing the math. The overhead of programmability, of fetching the instruction, decoding the instruction, fetching the operands, all the things that give you the programmability, which is so valuable for doing new models, new layers, doing different normalization schemes, doing sparsity masks, doing dropout, whatever you want to do, you can do with the programmability. You essentially get for free. It's not advancing. Okay, hello. I'll advance it this way. The Turing part, so Volta was announced in May of 2017. Turing we announced last summer in August of 2018. Does the same thing for inference. Volta is an inference GPU. Turing is actually a universal GPU. It matches Volta's performance, not this version. This is the T4, which is very low power and 65 teraflops FP16. The Quadro 8000 is 130 teraops of FP16. It's actually slightly faster than Volta. But what's key here is that we've also provided int8 and int4 tensor cores. So for inference, we can provide an enormous number of ops per watt for inference. In fact, it's quite a bit better than any of the special purpose parts that I've seen to date. And a little graphic of sort of how this works. Back in Pascal, we had a dot product instruction. So you could sort of do 4 operations at a time. With Volta, we went to the FP16 tensor cores that do 128 ops at a time. And then in int8, it's 256, and in int4, it's 512. So it just multiplies up the performance. And when you look, and these are the numbers for the FP16 version, the fully loaded cost of instruction fetch, decode, and operand fetch. And by the way, even in a tensor core, you have to get the operands from somewhere. And I have to say, I was not allowed to show the actual 12 nanometer numbers. So all these numbers are scaled from publicly available 45 nanometer numbers, running the RTL code through and getting the extracted energies out. But basically, the overhead of programmability is 27%. What that means is that if you threw everything else off the GPU except for the actual math units themselves, and of course, there's going to be some overhead even for a dedicated accelerator like a TPU, you couldn't do any better than 27% better. And that's assuming you can make floating point units as good as ours, and we've been at it for a while. Now, one thing I like to show is the evolution of our performance over the years. And this is the chart for inference. It's a comparable chart for training. And everybody always likes to compare against Kepler. It's kind of like the way they used to always compare against the VAX 11780 because it's a good target. But Kepler is a part that we started shipping. In fact, the K20 wasn't even the first one. But we started shipping the K20 in 2012. We completed a lot of the initial stages of this design in 2009. And that was sort of before we'd really identified deep learning as a target area to make things better. Even so, it was for a long period of time the platform people ran deep learning training on. And just to show you that Moore's law doesn't matter here, M40, which is in exactly the same technology, they're both TSMC 28 nanometer, we announced a couple years later with almost double the performance per watt. From there on, we went to Pascal. And by the way, these were both doing FP32 operations. We didn't have the FP16 until we moved to Pascal. The jump here is FP16 on Pascal. The color here, by the way, encodes it's the next process node. These three are all 16 nanometer. I know we call the last two 12, but it's 16 nanometer metal rules. So it's the same energy as the original 16 nanometers, just slightly faster transistors. But by going to FP16, we get a big jump, 3x in performance. By adding the tensor cores, still FP16, we get another big jump, about 5x. This is in efficiency, energy per op. And then adding the int8, this is for int8 inference, we get another huge jump. Now, Dave Patterson made the point this morning that the TPU1 compared against Kepler was 10x better something. I don't know exactly what they're measuring, may have been perf per watt. I will observe, and I'll show you the data on this in a couple slides, that they were comparing an int8 engine against an FP32 engine. And the difference between the energy to do an int8 multiply and an FP32 multiply is 16x. Almost the entire advantage of the TPU1 over Kepler is the difference between FP32 and int8. The rest of it is all just waving hands. This chart shows a similar thing for the single chip inference performance. But what really matters actually is the performance per watt, which this one is showing. And so over the past 6 years since we identified deep learning as an important use case, we've improved our performance per watt by 110x. We are not a stationary target. For all of these numerous startups out there who would like to eat our lunch, it's a very rapidly moving lunch. What's interesting is that the very same chip that is the leading chip for deep learning is also the chip that powers the most powerful supercomputer in the world, the Summit supercomputer at Oak Ridge National Laboratories, the most powerful supercomputer in Europe, Pisdaint, at the Swiss Federal Institute of Technology, and a large fraction of the top 20 on the top 500 list. Dave made the point of training at 200 petaflops. Summit is an exaflop machine. If you're going to count FP16 flops, it's 3 exaflops. And one of the winners of the Gordon Bell Prize at supercomputing last year, which included co-authors from both the DOE and from Nvidia, actually sustained over an exaflop on a deep learning task associated with interpreting weather patterns for climate change. So we've been able to sustain exaflop on real deep learning tasks using this machine. What's great about combining the FP64 performance you need for a lot of the historic HPC applications with the FP16 you need for deep learning is deep learning has revolutionized scientific computing in 2 ways. One is that Gordon Bell Prize shows by using deep learning to interpret the results. You run some huge climate simulation and you want the answer, is the Earth doomed? And the way to extract that is to look for things in that, to look for patterns of currents and typhoons and the like. And by finding those, you can actually interpret the results. It's hard for humans to find that in a huge data set. The deep learning, you can build pattern recognizers that find those things. The other application is actually doing the simulation itself. Rather than simulating the constituent equations, you can basically take previous simulations or real ground truth data and use them to train a neural network to predict the next state of the simulation. And people have gotten speedups as high as 10 to the 5th on quantum chemistry codes by taking the original density functional theory codes, taking results of them, training networks on them, and then running the networks and getting results that are equal accuracy with 10 to the 5th fewer operations. So this marriage of high-performance computing with deep learning is a huge thing. Now, in the embedded space, we make an SoC called Xaviar. It's designed primarily for our self-driving cars, but we also apply it to video analytics and robotics. And it's basically a tenth of a volt. It's got 512 volta cores instead of 5120, but it has a bunch of accelerators in addition to that. And so we have accelerators for video and things so we can process those 12 cameras coming in. But we also have a deep learning accelerator. And the reason we did this is in the embedded space, that 27% matters. And you actually want to get every little bit of overhead out of there. And so our deep learning accelerator actually looks a lot like the Google TPU. It has a big MAC array in the middle. It's not quite as big as theirs. It's 2K int8 multiplies per cycle rather than 64K. But it has two things that their deep learning accelerators don't have. One is it has support for sparsity, because as I'll talk about in a minute, most networks are sparse and the activations are sparse. And by moving around only the non-zero values, you can save an enormous amount of bandwidth. And by not burning any energy trying to multiply things by 0, you can save an enormous amount of energy. We also support Winograd transforms natively. And this basically makes convolutions much more efficient. If I have to do a 3x3 convolution and I do it in the spatial domain, it takes 9 multiplies. If I go to a transform domain, I can do that convolution with a single multiply. And so there's a big advantage for moving to the Winograd domain. So let's talk about MLPerf. So when I was a teenager, we used to race cars, and you only knew if somebody was serious if they would race you for pink slips. And so I think we should have raced Google for pink slips on this one. Basically, there were 7 categories. We submitted to 6 of them. The reinforcement learning category wasn't really appropriate for what GPUs are very good at. But the 6 we submitted to, we won, both for single node and for scalability. And it was really the scalability one that mattered. The Intel person mentioned the recommender system as being their submission was 1.6 times better than Pascal. So I went to the MLPerf site. And by the way, it's mlperf.org. You guys can all just go there and look the numbers up for yourself. Our submission was 116 times a P100, just to put that in perspective. And that's training it in 0.4 minutes. By the way, that trained fast enough that we didn't do multi-node for that one. It didn't make any sense. If you're taking, what is that, 20 seconds or something like that to do the training, you don't need to make it go faster by going to multiple nodes. So these are all in a single DGX2H. You guys can just get out your checkbooks and buy one right now if you wanted. You can take orders after the talk. If this isn't fast enough for you, these are the numbers at scale. We got very, very good performance speed-ups. And these are in a bunch of different clusters, most of which are clusters of actually DGX1s, because we just had a larger cluster of those available at the time we ran these to run on. But we got very good scalability on all of these because of our NVLink network and then the within the DGX1 and then the InfiniBand network connecting the nodes together. So this is where we are today, where we are the fastest in the world at training networks, at least as reported by MLPerf. We submitted to more categories than anybody else. We submitted to 616. Let's talk about where we go from here. We feel this responsibility, since deep learning is gated by performance and hardware, to keep those curves I showed you going, right? And we actually have pretty much the next 2 points on those curves pretty much loaded already, and we are still going up at a comparable rate. But where's that performance going to come from? And so some of the previous speakers hinted at this. One is from number representation. And when you choose a number representation, what you're really doing is you're selecting 2 things. One is how much dynamic range do you have and how much accuracy do you have? And it's important to use as few bits as you can for 2 reasons. One is that the energy goes quadratically with the number of bits, right? When you do a multiplier, going from doing an 8-bit multiplier to a 32-bit multiplier is not 4 times more energy, it's 16 times more energy. Again, that was the entire difference in energy between the TPU1 and a K80, is comparing int8 with FP32. But the other reason it's really important is that you want your data to be small, both the weights and the activations, so that you can fit a lot of it in whatever on-chip memory you have and keep it right next to the arithmetic units, because moving data around is very expensive energetically. And so one thing you want to do is to look at ways of encoding your data that makes the most of each bit. A bit is a horrible thing to waste. And this shows, after pruning, which I'll talk about in a minute, the distribution of weight values in a network. I believe it was in VGG16. And what you see here is that if I have 4 bits to use, I could choose to use them with an integer representation, which would give me the evenly spaced symbols as shown by the green X's here. And you can see that's a horrible way to waste your symbols, right? Because I've got a bunch of symbols out here where nothing is happening, and I'm sampling the place where everything is happening very sparsely. A better way to use your symbols, if you have 16 symbols, is to do what the red dots show here, is to put them very densely where the interesting things are happening and not waste any out here for the outliers. And the data here is from a paper that I published with my former graduate student, Song Han, who's now a professor at MIT in ICLR, actually in 2016. It went on archive in 2015. And this is one way of doing it. It turns out this is actually an energetically inefficient way of doing it because it requires a codebook lookup and a full 16-bit multiply. There are actually very clever numerical encodings. They get you a similar efficiency. We can wind up getting 8-bit accuracy with sort of 4 bits per symbol and do it in a very energetically efficient way. This is another figure from that 2015 paper, which shows, for convolutional neural networks, we're able to get down to 6 bits per symbol with no loss of accuracy. That's no loss of accuracy compared to FP32. And for fully connected layers, for multilayer perceptrons, we're able to get down to 4 with no loss of accuracy. You don't really fall off a cliff of accuracy until 2 bits. And actually, since this time, we've done a lot of work that is not published yet, which is actually even better. So you can use the minimum number of bits required, and that number is trending down toward 4. A lot of people will say, let's go binary, and it turns out that winds up not being such a great idea. You wind up losing more accuracy and having to earn it back in ways that are more expensive, and 4 seems to be kind of the sweet spot in energy for doing things, to get a given level of accuracy for inference. So let's talk about pruning. One of my favorite sayings in life is never put off till tomorrow what you can put off forever. And this goes especially true for multiplies. So it turns out that just as biological brains are sparse, right? They do not have every neuron connected to every neuron, and then they're even sparser dynamically in terms of where the firing occurs. Artificial brains can be the same way, and in fact, you can lop out most of the neurons in a network and not lose any accuracy. For fully connected layers, we've been able to repeatedly knock out 90% of the neurons, leaving only 10% remaining with no loss of accuracy, and for convolutional networks, between 60 and 70% can be pruned, leaving 30 to 40%. Now to do this, you then have to retrain the network, right? So what you do is you train the network, you then lobotomize it, lopping out some large number of its neurons, and you get performance that's indicated by this purple line here, right? So Dave, I think, said a 1% loss of accuracy is considered catastrophic. We actually consider a 0.1% loss of accuracy catastrophic. And so we would stop pruning at around 50% without retraining. But with retraining, we get the green line here, where we can get out to easily over 80% without substantial loss of accuracy. And then anything that's fun doing once, you should do multiple times, and that's true for pruning as well. So if you iteratively prune, you prune to one level, retrain, prune, and retrain. After 3 iterations, you get the red line here, where we're out to 90% pruning out, 10% density left without loss of accuracy. And again, the reason why this is really important, this combination of reducing precision with pruning, is it lets us fit things into a really small local memory. And the cost of accessing memory goes up an order of magnitude every time you move up the memory hierarchy. So if I can fetch my data from a really small local memory, that's 5 picojoules per word. If I have to go across the chip to get it from SRAM that's on chip but not really local, that's 50. By the way, this memory is built out of a bunch of these little memories, and the other 45 is crossing wires to get there and back. It's the communication that really burns the energy. And if I have to go off chip, even with LPDDR, which is a very energy efficient memory, it's yet another order of magnitude. So let me switch gear here and talk a little bit about deep learning accelerators. We've been building these in Nvidia research for a number of years. Let me talk about a few. The first is one that I actually did with a number of my colleagues at Stanford, the EIE. And the reason we did this is we were playing with these sparse networks, and the conventional wisdom from every person we talked to, especially the numerical analysts, was you're in the uncomfortable range of sparsity. So it turns out that most people have sparse matrix packages. We have one called cuSparse. And cuSparse starts beating cuBLAS at a sparsity level of about 0.5%. In other words, if you're 0.5% dense, you're better off using the sparse matrix package. Denser than that, you're actually better off just doing the dense calculation. And we're in this range of 10 to 30%, depending on whether you're an MLP or or a convolutional network. So what we said is, OK, that's great if you're running on conventional hardware, but we can make sparsity work by building a pipeline where we basically walk the compressed sparse column structure in hardware. It takes almost no area, almost no energy to do this. And this is the beauty of domain-specific hardware. We can wire in things that do that. So we basically did this accelerator to show that we could make sparsity and that trained quantization. There's a code book look up here where it says weight decoder, essentially for free, and show people, yes, when you're building the hardware, you can do things that are not possible if you're just writing code. One thing that's really interesting to me looking at this plot, which is the EIE was an array of processing elements, and looking at each processing element is it's all RAM, right? The non-RAM stuff is this little thing in the middle labeled arithmetic. And this is actually true of many accelerators. They tend to be completely memory dominated. In this case, the memory is needed to hold the sparse matrix and to hold that compressed sparse column structure that has the pointers into the sparse matrix. So with EIE, we showed we could do sparsity really well for fully connected layers. We then, in Nvidia Research, did a project called SCNN, where we looked at the problem for convolutional layers, where you have an activation layer that looks kind of like this. It's got maybe, after applying ReLU, all the negatives turn to 0. And so you wind up with maybe 30 to 40% non-zeros. We're convolving that with, after pruning, a kernel of weights that looks like this. And of course, it fills in almost completely until you apply the ReLU again, and then that red one will look like this. And so we looked at the most efficient way to do this. And the approach we took in the SCNN was basically just to read a bunch of weights. So we basically pack the green, so only the green ones are there. We get rid of all the white, but with each green square, we have its coordinates, x and y. Similarly for the this. And every one of these green squares has to be multiplied by every one of those blue squares. So we just do that. We read W weights at a time, M inputs at a time, and I think it was 4 and 4 for the baseline configuration. We multiply every one by every one, so we produce 16 products, and then we sort them all out on the output by taking their coordinates, adding the coordinates together, and that basically says where to accumulate the results. This wound up giving about a 3x boost in energy efficiency over running the computation dense. So we're looking at where we're going to get the next 10x. You can get a lot from better number representation. There's probably a 3x in there from sparsity. There's some other things. This is actually a die that we just got back recently. We're experimenting with a bunch of things. One of them is scalability. So it's actually a 36-die MCM. And on each of the locations in the MCM, we have an array of 16 processing elements. And so we can scale this from a single processing element, which you could use for some small IoT device, to something which does something in excess of 2,000 images per second on ResNet 50, batch size 1. And its energy efficiency is 105 femtojoules per op. So about 50 teraops, 50 teramax, but excuse me, I'm confusing this with a later one. This is, about 10 teraops per watt for doing 8-bit deep learning inference. And so this demonstrates a bunch of neat technologies for communicating between the MCMs. But where it's getting a lot of its performance for the deep learning comes from is partitioning the weights and activations so that things stay local. So the weights are actually local on each block. We take the input activations and partition them by row, both over the chips of the MCM and the PEs of the array per MCM, and then partition the output activations by column. So everything is very local communication flowing through the system. More recently, we've done a study of doing this type of tiling, as numerical analysts call it, at multiple levels, where in addition to sort of reading out of a very small weight buffer, we actually have a weight collector. It's like a 4 or 8 element thing that holds just a few weights. And by doing this, I'm going to jump forward just to getting a little bit behind my schedule here. We're able to demonstrate, and again, in the same technology, these are all 16 nanometer numbers, 30 teraops per watt on inference. And so we're constantly trying to raise that bar ourselves to see where we're going to get that next jump in inference performance. One of the things that's not even in this chip yet, but we're looking very carefully at, is making the on-chip communication more efficient. Remember, moving this data around is really expensive. And one way of doing this is to use every electron twice. So normally you start at the power supply. That's like 0.8 or 1 volt. And you get to use that electron once as it drops to ground to signal a 1 or a 0 through an inverter. What we do here is we introduce a mid-plane, which is half the supply voltage. So this is 0.8, that's 0.4. We get to use the electron once on the top floor. sending this bit across. We use it again on the bottom 4, sending this bit across. And we actually gain 4x by doing this because the energy goes as the square of the voltage. Seems like you're getting something for free here. It ought to be 2x, but it's actually 4. There's a paper on this at ISSCC in 2016. And again, it's one of the cards we have on the table to keep those plots going upward. So I kept on getting pestered by our board members about analog because many of them had invested in these various startups doing analog deep learning. So I did what I usually do is I go over and I talk to my colleagues at Stanford. And in fact, Boris Merman is a great resource on this. He's done about a lot of analog neural network chips. And after talking to him for a couple hours, I realized that it's all about the data conversion. So even if I spot all these people that they can do really efficient vector matrix multiply in analog by taking a vector of activations as voltages, a matrix of weights as conductances, and applying Ohm's law to get current equal conductance times voltage, I'm going to give that to them for free and charge them only for the cost of doing the data conversion back at the end of the layer. But I'm going to be very scrupulous about precision. If you want to match 8-bit inference performance, you have to do the data conversion with enough bits that you're not, after you've summed up a bunch of things, you're not throwing away significant bits. So it turns out that Boris actually maintains this database of all the analog to digital converters anybody has ever done. That's all the points on this chart. And it turns out that they're bounded by 2 fundamental limits. It costs something to do a conversion no matter how many bits it is. And then it costs exponentially more to do conversions as the number of bits goes up above about 10. And so if you take that data, you assume that the multiplies are free, but you still have to do a conversion per layer. And you allow, turns out that you can sum as many multiplies together before you do the conversion. You can't win that way. And this is one of the ways that physics just works amazingly well. However many you have to sum together here, you just wind up needing more bits of precision by exactly the same slope. So you wind up on the same line. And it turns out that to match 8-bit inference performance takes over a picojoule per Mach. Remember, we have demonstrated in chips that are in the lab right now 200 femtojoules per Mach. So they're off by a factor of 5 there. Not counting the energy they're using to do the multiply and everything else in the system, just doing the A to D conversion. The thing that's interesting, though, is if you start walking up some of these, if you went from 8 to 7 to 6 to 5, around 4 or 3 bits of precision, analog might make sense. Of course, at that level, the digital is a lot less expensive as well. Remember, we're getting 70 femtojoule per Mach in that one chip that I showed you a little while back digitally. Now, one reason we're able to keep pushing the edge on deep learning hardware at Nvidia is that we eat our own dog food. And so we have a big research organization that takes our deep learning hardware and frameworks and software at each level and tries to push the state of the art with it. So we have among the best semantic segmentation systems. We have currently the top of the leaderboard in optical flow. This is actually a very interesting network. I encourage you to go to the CVPR paper last year because it did not take the end-to-end approach, which many people took for deep learning optical flow. Instead, we took 20 years of computer vision research in optical flow, took the best ideas of how to do optical flow without deep learning and applied deep learning to them, and wound up getting really kind of the best of both worlds. And then because we need to process LiDAR data from our self-driving cars, we have among the best 3D segmentation for point clouds. Now, our core business is graphics, so we also have made the practice of applying AI to graphics. And this comes in really 2 main categories, and I only talk a little bit about one, which is content creation. A lot of people don't appreciate it, but the video game industry is a bigger industry than the motion picture industry by revenue. And typically, producing a AAA video game costs significantly more than producing a major motion picture. Most of the AAA titles break $1 billion. And most of that money goes to artists. It's artist time. And so the key thing to enable the industry to do more is to automate content creation. These are some figures out of a paper we had with people at one of the game developers, where instead of having, if you wanted to animate a face, they would typically have what's called a rig with about 300 control points to move different muscles of the face. And producing something like a 10-second segment would take about 3 weeks of artist time, laboriously controlling the rig until it looked correct. What we did is we trained a neural network with an actor, and then we're able to take an audio trace to animate the face speaking. And in a double-blind experiment, you couldn't tell it from the one that somebody spent 3 weeks producing. And it basically ran in a few seconds on a GPU. The other 3 here I'll talk about in a little more detail. This never works, and so I have the backup queued up if I can only, oh, I see, I've got to select that, and then I need to mirror my displays, and you should see this. So this is how we take the tensor cores on Turing and make them useful for graphics. Everybody in deep learning is always worried about the tiny little bit of area we have devoted to graphics and that it doesn't make deep learning faster. We're always worried about the other thing, which is all the area we devote to deep learning that doesn't make graphics faster. This is the technology that I'm very happy about because we developed it in NV Research, which is the organization I run. It's called deep learning superscaling. And so what we do is we take this image and we actually render it at one resolution and then feed it into a deep network that up resolutions it. The typical case is 1440p to 4K because this is an HD monitor. I believe this is 720p to HD. And you can't really appreciate it until I run this slider across. But the DLSS on is on the left. And so you see how things to the left of this, like those little features on the back of this booth, just pop out when the slider goes across them, or these little glass ornaments. You can't really see what's inside them until you turn the DLSS on going over it. So this is one great way of taking deep learning performance and making graphics better. Now, I'm showing you the easy case here with a still image. Anybody can do a still image. What makes this hard is that if you apply this to a video sequence and you're hallucinating those pixels that were never shaded, you have to do that consistently frame to frame, or it looks really, really objectionable. You get little wigglies, and you get things flashing on and off, and that's a no-no. You will get drummed out very, very quickly if you do that. So let's go back to the main talk, extend desktop. Why is that not coming back? That is bad. Let's try this again. So let me go back to here. Okay. It keeps coming back to that. There we go. Well, I've got this here, but I don't have it over there. Let me just, if it works, reboot it. The other thing I can do is just quit the thing that's taken over. So let me go back to here. And I will quit that. Hold that to quit. OK. Now it will give me control back, I hope. This is another example of how to apply deep learning to graphics. So if you watch a major motion picture that's either animated or one that's live action but has CGI segments in it, the artificial portions of it are done with a technique called ray tracing, where you actually cast rays from the eyeball into the scene, see what they bounce off of, and then ultimately you try to, after many bounces, connect them to a light source and then run that backwards to compute what color you get. A major motion picture will probably cast about 10,000 rays per pixel. And that will take many hours on a farm of hundreds to thousands of CPUs. We don't have many hours or hundreds of thousands of CPUs. We have one GPU and 16 milliseconds. So what we do is we cast 5 rays per pixel, and we get an image that looks kind of like this. So this looks like what your camera would take if you set your ISO to like 200,000. Right? It's a very grainy, noisy image. And then we feed it through a deep neural network, and we get this beautiful image. Again, double-blind experiments, people can't tell the difference. And this is what's enabled us with our RTX technology to bring ray tracing and physically based rendering to real-time graphics. We couldn't do it if we had to do 10,000 rays per pixel. But if we can do a few rays per pixel and clean it up with a deep network, it makes a whole nother level of realism in graphics possible. We've also been doing a lot of work with GANs. About a year ago, we developed this technology called progressive GAN. And the thing we realized is that and again, we have these two networks. We have the generator network here and the discriminator network. The generator network's never seen a picture of somebody. All it sees are these random variables called latent variables we feed in. It produces a picture, and it gets one bit of feedback, good or bad, right? Good, you fooled me. I thought that was a real person, or bad, that's obviously a fake. By the discriminator network, which is trying to learn at the same time. And nobody, before we'd done this, had been able to do good high-resolution images. They started getting blurry. And the reason is you just have too many free variables. You've got this huge generator network and huge discriminator network initialized to random variables, all trying to learn the stuff with neither having any idea of what it's doing. So we thought about this. We realized the right way to do this is the way you would teach a kid mathematics. You don't start with differential geometry and give them the big black hole and tell them about general relativity, you start with arithmetic or maybe set theory or something like that and work your way up. So we started with a very simple network. We'll learn 4 by 4, and the discriminator will discriminate 4 by 4. And when it gets 4 by 4 right, we'll move up to 8 by 8, and then 16 by 16, and so on. And by doing this in a progressive way, what's often called curricular training, we're able to get the network to be stable and converge something that produces really good high-resolution images. Here's the movie of the training. It shows the resolution it's training currently at the bottom left, and the number of days, I think, on a single V100 in the middle. And you see that by the time it gets 256 by 256, the images are looking pretty good. We can go up to 1,000 by 1,000, and the images are still crisp, even though, remember, this generator has actually never seen a picture of a real person. All it's getting is feedback about whether the image it's produced is real or fake. Now, just recently, we improved on this significantly by developing a new network called StyleGAN. And what we show here on the left side is sort of the way our progressive GAN and most GANs work. We feed the latent variable in the top, and your image comes out the bottom. And it's kind of a flow down between the layers. Well, it turns out that we can get much better results if we don't do it that way. Instead, we just feed a constant into the top. And instead, we take our latent variable, and we feed it to a multilayer perceptron, and then we factor it into pieces we feed into different resolutions. And by doing this, we can take different parts of the latent variable and use them to control different aspects of the image we're producing. We can control different resolutions, different aspects of the face. So we can independently control things like hair color, eyes, teeth, and the like. These are our images coming out of the StyleGAN as we interpret that latent variable at different scales. Let me see how we're doing on time here. Okay. So let me wrap up. Actually, yes, I'm ahead of time. That's amazing. So deep learning has fueled a revolution in almost every aspect of our life: transportation, healthcare, education, and graphics. And as a hardware designer, I'm really happy about this because it's been enabled by hardware. It's been this co-design between hardware and algorithms. But the core algorithms have been around for 30 years, waiting for the hardware to catch up with them. And so it's kind of great that the hardware finally did. And now that we're here, progress is gated by hardware. If we don't continue to build faster and more efficient hardware, we will plateau. We will stagnate because we can't run bigger models on bigger networks without better machines to run them on. So we've been able to increase the performance of GPUs probably by an average of about 3x per generation since the Kepler generation without any help from Moore's law. Right? We had one process jump in there where we jumped from 28 to 16 nanometer. That gave us maybe 20%. It didn't help much on that 3x. And it's been by being clever about architecture and circuits, going from doing FP32 on Volta to doing int8 on Turing, but also adding the dot product instructions and the tensor cores and a lot of other features that have been geared toward deep learning. And that's where we get today with Volta at 125 teraflops for training, and Turing at 261 teraops. That's a Quadro 8000 of int8 and 512 teraflops of int4. And at int4, we're about 3.6 teraflops per watt for inference. For embedded systems, we have Xaviar SoC, which has 20 teraops of deep learning performance, part of which is in the Volta cores, part of which is in 2 deep learning accelerators. By the way, the deep learning accelerator is open source. You can go to mvdla.org, download the RTL. Many people are using it in their own SoCs. And the question now, and what I sort of wake up very excited about working on every morning, is how do we continue scaling this performance from actually this pretty impressive point we're at today without any help from Moore's law? And I've shared with you some of the things we're going to be doing. Precision. We need to use the fewest number of bits that we can and make each of those bits count, which means we don't do linear sampling. But we need to do it in a way that the arithmetic operations are efficient. We can't afford codebook lookups and high precision multiplies like our original trained quantization work. We need to move to supporting sparsity better. We already support sparsity quite well in our DLA, by the way, which has support for sparsity in both data gating of the multiplier array and in all the data transfers being in compressed form with the zeros squeezed out. And then accelerators are really sort of how we're prototyping a bunch of these concepts, but with the idea that in the long run, they'll go both into future versions of the DLA and future tensor cores that would then support new data types, support sparsity, and other things going forward. Now, what keeps us honest about this is we use our own stuff. We eat our own dog food. And I'll give you some examples of how we apply deep learning to perception, to graphics, and to image synthesis. And with that, I'd be happy to take some questions.
We have lots of time for questions, and I'm sure there will be many. This one. Oh, no.
Take one. So to what extent do you feel like the restriction or gating on the performance is due to the GPU versus not owning the host processor?
Oh, so to what extent is the gating on performance due to the GPU not owning the host processor? So very little. When we first started doing some image work, we wound up being a little bit limited by the host processor, doing things like decoding the JPEG and shuffling the images, because when you do the epics, you need to have each batch be independently sampled. And so we moved all that to the GPU with our package called Dolly. And now we're not constrained. So like in a DGX 2, where we have, I think, two pretty good Xeons, those are not the gating factor. I mean, it's GPU limited.
Got it. Thank you.
Yeah.
Actually, an announcement to make. There's a lost wallet named Chemlal Salam at registration, just so you know. Yeah. And I believe, so Bill is here. If you have any other questions, please come up and talk to him. We're now going to coffee break. We're back at 3:30 p.m., so we have 45 minutes, and see you then. Thanks. Oh, one question over there, sorry.
Okay.
Yeah, so I have one question about the architecture. So you mentioned about Moore's, you and Dave both mentioned that the Moore's law is going away, and is there any, it's basically now up to the architecture, and what do you foresee the Moore's law of architecture? Like, is there something do you foresee in future happen to the archicture as that happened to similar to the processor?
Yeah, that's a great question. So, unfortunately, what was great about Moore's law and Dennard scaling even more so, it was sort of the gift that kept giving, right? Every generation, you'd shrink line widths and everything would get more efficient. And you'd be able to turn some of that efficiency into better performance. And Moore's law, which is really about the economics of semiconductor manufacturing, said every generation the transistors get cheaper, and then the next generation they got cheaper again. The problem with architecture is every clever idea you think up as an architect is a one-time play. You play that card and it's played, right? You add tensor cores. Okay, we've played the tensor core card. What are we going to do next time? Now, I think that the one trend, and I think Dave said it as well, is that we're moving to more domain-specific architectures because we can get more efficiency that way. But even saying that, each thing you do with the domain-specific architecture is still a one-time play, right? So to continue to scale performance, to get the 3 to 5x we've been giving you on every generation of GPU for deep learning, the really easy, obvious ideas have been done, right? We have to think of the harder, less obvious ideas and just have a lot of smart people trying a lot of things and seeing what works. And eventually we'll reach the point of diminishing returns where it gets harder to find those things. Right now we're not at that point. We have lots of good ideas. We can see our way through the next several data points, but it will get harder as time goes on.
Thank you.
We're warming up on questions now. Go ahead, please.
You mentioned that some of the compression methods that require table lookup for the weights are not energy efficient. Can you elaborate a bit more on that?
Yeah, so the paper that Sung Han and I published at iClear in 2016, we basically wanted to find out what sort of theoretically were the fewest bits we could use to quantize a weight. So we observed, as many people have, that anything you can differentiate, you can train using backprop. And so we basically did backprop into our code book and trained a code book to basically find the optimal set of weights, given a number of weights, to represent the weights. And to do this, you had to do some k-means clustering to group the weights together and then backprop to what value would do that. Now, the reason it's not energetically efficient is if you look at what you have to do now to do the arithmetic operation. First, you have to do a lookup from a small table. Right? We use a latch array for that, so it's not as bad as the 2.5 picojoules we'd use reading 16 bits from a RAM, but it still winds up being hundreds of femtojoules. And then we have to do a 16-bit multiply because decoding the way we decoded it to 16 bits, so we wouldn't lose any accuracy there. And that 16-bit multiply is 4 times as expensive as doing an 8-bit multiply. So that pipeline of table lookup 16-bit multiply is a very expensive thing. So it turns out that if you really want to use a small number of bits efficiently, you need to come up with a numeric representation which samples non-uniformly, putting the bits, most of the symbols where the interesting things happen, but also admits very inexpensive arithmetic. And there are such things, but I'm not prepared to talk about them yet.
In general, if you have questions, please go up to the microphones. I think part of the confusion with questions has been there are 3 microphones, 1, 2, 3. If you have questions, please go there.
Yeah.
How do you see the advent of non-volatile memory changing the GPU landscape? Things like register technology, stuff like that.
I don't see any really substantial change there. We're always looking for better memory technologies. We have many active collaborations going on with the major memory companies. And so we'll take what we can get in either more capacity, fewer dollars per bit. What really matters to us, though, is bandwidth and energy per bit, moving the data on and off. And I don't see the non-volatile memories making a big dent there. Many people are applying non-volatile technology, both flash and memristor, to trying to do these analog multiplies. And so we kicked off a project to try to replicate some of those results. And the result of that was this paper that will be in DAC this year, which I showed 2 figures from, where we found that we were completely dominated by the A to D converters. And that, using a given noise model, we wound up with energy per bit for certain accuracy levels substantially higher than what we could do with digital.
GPUs are virtualized now. And so what are the techniques being used to make the context switching times smaller and smaller?
So they're virtualized now, but the context switching time is not very small, nor do we feel a lot of pressure for it to be small, because we don't do a lot of very rapid context switching.
OK. So what's the order of
I would have to get, I don't have that on the top of my head.
Okay.
I would have to get that number for you. Yeah.
Let's thank Bill one more time. Thanks, Bill.